truth tables provide a way of evaluating deductive arguments. Whether or not they are valid or invalid can be revealed by a truth table. So these don't apply to inductive arguments, but this is a very helpful tool for evaluating deductive arguments. So I want to make a couple points, and then we're going to go through 3 examples. So in order to check the validity of an argument, you can construct a truth table, and then that's going to have corresponding truth values of all the premises and the conclusion. And what we do is we consider all possibilities, all possible scenarios, with each individual statement being true or false. So we'll see that as we develop a table. And if the truth table reveals that all the situations in which the premises are true are also situations in which the conclusion is true, then we have a valid argument, and the truth table demonstrates that. That fits our definition of validity. Now, if there is one or more possible situation in which we have all of the premises being true, but the conclusion is false, then that does not fit our definition of validity, and the argument is invalid. So this is a great way, a simple way of testing whether or not an argument is valid or invalid. And we'll look at 3 examples. So here's the first example, a disjunctive syllogism. Let's say here the P is the statement the plant has sunlight, Q is the statement the plant has indirect light, and we just have it either has sunlight or indirect light. It does not have indirect light, therefore it has sunlight. Sounds like a reasonable argument. Let's put it to the test with a truth table. So in order to evaluate, what we're going to need is a representation of each of the premises and the conclusion. And first we have to cover all possibilities of truth values for the sentence letters P and Q. And the traditional way of doing this is, when we only have 2 sentence letters, is we just go down the first column, true, true, false, false. And on the second column, we have true, false, as we go down with the Q. And that way we have all possible scenarios, both being true at the top, both being false at the bottom, P true, Q false, P false, and Q true for the second and third rows. So now one of our premises was not Q. It's not the case that Q. And so that's going to have the opposite truth value of what we have in the column under the Q. So when Q has true, not Q is false. When Q is false, not Q is true. And so we can complete the column in that way. Now we have a premise that is P or Q. That was one of our premises. And so we have to look back at our first 2 columns and see whether or not P or Q is true. And that's going to be the case when either one of them is true. So when they're both true, P or Q is true. P is true in the second scenario, so P or Q is true. Q is true in the third scenario, so P or Q is true there. And the only case where P or Q is not true is when both P and Q are false, and so that letter is false. Now our conclusion for this argument was simply P. And so I've restated that over here. You really don't need this additional column, but just to point out that we're looking at P as the premise, we just repeat that first column. So we have true, true, false, false. And in this case, it is valid. So let's think this through and make sure that we see how it's valid. We want to look for any cases where all the premises are true. So in red, we have the premises. The only case in which the premises are both true is in that second row, and that's a case where the conclusion is also true, and so we have a valid deductive argument. The disjunctive syllogism is a valid argument form. Our second argument example is that of denying the antecedent. So we also we have this if P then Q, not P, therefore not Q. Now this sounds reasonable to many people. Say P is Tom goes to the store and Q is Tom gets milk. So we have if Tom goes to the store, then Tom gets milk. Tom does not go to the store, therefore Tom does not get milk. Seems reasonable. Let's check it out with the truth table. So we have our P's and Q's, and again, we set them up in our standard fashion with true, true, false, false in the P column, true, false in the Q column. And now we go through and we fill out the premises. If P then Q is our first premise, and if P and Q are both true, that's true. But when P is true and Q is false, if P then Q is false. And in the other situations, the standard way of doing this is if P is false, then if P then Q is false. You can refer back to filling out a truth table for conditional sentences to review that. Okay, our second premise is not P, so it's going to be the opposite of our first column. So we have false, false, and then where P is false, we have not P is true, so the bottom two are true. And then we have not Q, of course, which is going to be the opposite of whatever Q is, and since Q is true in the first case, not Q is false. Q is false in the second case, not Q is true, and then that is repeated where we have the opposite values. Now, this seemed like a reasonable argument, but we see that it is in fact invalid. Why? Because in that third row down, we have both premises being true. Our first premise, if P then Q, is true. Our second premise, not P, is true. But our conclusion, not Q, is false. So this seemed like it might be good reasoning, but in fact it is not. Let's think through it again with our statements. If Tom goes to the store, then Tom gets milk. Tom does not go to the store, therefore Tom does not get milk. Tom could have gone to a gas station and picked up milk, which typically wouldn't be considered a store, say, for example. Maybe borrowed milk from a neighbor and got milk that way. So it's possible for not Q to be false, even with the premises true. That tells us that that's an invalid argument. Finally, let's look at a third argument form, denying the consequence, sometimes called modus tollens. And we have a conditional statement, if P then Q, not Q is a premise, we conclude not P. So we could use the same statements as before. P is Tom goes to the store, Q is Tom gets milk. So if Tom goes to the store, then Tom will get milk. Tom does not get milk, therefore Tom does not go to the store. Let's check this with our truth table. We have the same standard ways of completing the first two columns. We have if P then Q. We did that in the last truth table, so we know how that goes. It's going to be true in every case except the second one where we have P being true and Q being false. And then not Q is going to be the opposite of Q. So instead of true, false, we have false, true, false, true. And then the same for not P in relation to the first column. So instead of true, true, we have false, false. And instead of false, false, we have true, true. And here we can see that the argument is valid. The only case where we have both premises are true is in that fourth scenario. So we have true premise and true premise. And in that case is one in which not P is also true. And so this is a valid argument form. So that's how you use truth tables. You can do this. We can expand this. We can add additional letters. Those are your basics for completing a truth table and assessing whether or not an argument is valid or invalid.